Hello and welcome to ChemAxon's ChemInfo Stories webcast. My name is János Fehérváry and I am head of marketing at ChemAxon, hosting today's virtual event. Today, two of my colleagues will walk you through the topic of prediction-driven design of hERG liability-free compounds. First, please welcome Ákos Tarcsay on the virtual stage. He received his PhD in 2014 in the field of computational chemistry with special focus on drug design applications. He has 6 years pharmaceutical research experience with more than 15 publications. He joined ChemAxon 6 years ago as a senior application scientist, and currently he is the product manager of calculators and discovery tools who developed the ADMET plugin group. Ákos, it is your turn now.
Welcome to this episode of the webcast series. Our topic is the prediction-driven design of hERG liability-free compounds. I will start with a brief introduction of the topic by reviewing literature findings, especially for the physical-chemical property correlation with the hERG binding. Then I will introduce you the ChemAxon hERG model and show you benchmarking results. And finally, we will put this into a context how the model can be utilized in a drug discovery pipeline. hERG ion channels are potassium channels responsible for the repolarization and contributing to the T peak of the electrocardiogram. Inhibition of the hERG ion channel will result in QT interval elongation and can cause arrhythmia and sudden death. Surprisingly, diverse set of drugs can block the ion channel, and this side effect is a common reason for drug failure in preclinical safety trials. Due to its immense importance, FDA recommends early screening mitigation of the risk using in vitro techniques. And among the techniques for the safety risk mitigation, they are recommending electrophysiology as the most important endpoints to be followed. hERG ion channel is composed of 4 subunits, and the central cavity is electronegative. The binding site itself is covered by lipophilic side-chained amino acids, valine, phenylalanine, or tyrosine. It can orient the ligands in different positions, and therefore radioligand binding studies might not always correlate with the electrophysiological readouts. In the literature, multiple binding sites were recommended. Some of the molecules might bound from the membrane surface of the ion channel if they have high lipophilicity. And the molecules tend to have positive charge, similarly to the potassium ions, and tend to have high lipophilicity due to the nature of the cavity itself. This was strengthened by large data analysis published a decade ago in the ADME and TOX rule of thumbs, where it was observed that as the molecular weight increases, there is a higher chance to obtain mean P activity higher and higher. Ionization state was also found to be a characteristic property for hERG inhibition. Neutral and acidic molecules tend to have lower P activity and lower chance or risk of hERG inhibition. Basic molecules are the most risky category, and zeta ions are in between neutral and acidic molecules. If you break down the ionization state data by log P, calculated log P values, calculated octanol water partitioning coefficient data, it is obvious that molecules with low lipophilicity will have lower chance to inhibit the hERG ion channel. Molecules in between 3 and 5 will have higher, and the highest risk category is observed even for bases when the molecules tend to have higher than 5 log P values. The curve is quite similar, but the effect of the lipophilicity can be clearly seen on this data. If you are checking the transformations from a hydrogen to another moiety from this literature example, if the transformation introduces higher lipophilicity, as measured with the delta C log D value, in the pie charts, you can observe the chance to be a hERG blocker increases, as opposed to introduction of polar moieties, where the C log D decreases, and in this correlation, as you can see, the modified versus the hydrogen alternative PIC50 value will decrease. But not only physical-chemical property changes were analyzed in the literature, but matched molecular pair results, which also showed similar tendencies. Changing a hydrogen to an OH will have a positive effect, since the observations will be decreased P activity value or neutral. But changing a hydrogen to a phenyl group, you will have higher chance to be a more hERG risky compound. At the end of the day, changing a chlorine to methoxy also contributes to more hERG safe profile of your drugs. We also checked Campbell data, focusing on the patch clamp subset 2 years ago, and that was published in an earlier webcast, what you can watch on this YouTube video link. And we plotted the absolute median delta values against the standard deviation. And as you can see, in these cases where more than 5 observations were in one of the transformations, the structural modifications have high variance, although some trends can be clearly deduced from this analysis. Changing a hydrogen to phenyl also increased drastically the hERG inhibition. Changing a carboxylic to an ester, ethyl ester, or methyl ester also increased the hERG affinity. Changing a methyl to a more bulkier substituent also increased the hERG affinity. So MMP results also are in line with the physical-chemical property related changes. But in the medicinal chemistry literature, 4 strategies are mentioned to avoid hERG risk. One of them is the pK attenuation, changing the basicity of the molecule by introducing further substituents. The second strategy is controlling the lipophilicity by adding polar atoms and moieties. Or you can introduce a negative charge if the primary target SAR allows. And the last is the discrete structural modifications. Since there are cases when within a series of molecules, neither pK attenuation nor lipophilicity control resulted in more hERG safe molecules. In this case, trial and error changes and serendipity plays a role, since the binding sites can accommodate the ligands in different orientations, but some of the modifications will result in clash with the hERG ion channel and will decrease the hERG binding affinity. For learning and for data-based techniques, we need curated data. And as it was shown recently, the different measurement methods are correlating quite high with each other. Here, in flux assay versus Campbell assay, a correlation is shown, and Campbell any assay versus the patch clamp assay. But as you can see, the highest correlation that was observed was 0.88. And this will be the top limit of what can be achieved with the modeling technique if you mix up these results. Therefore, we decided to use only patch clamp data to be able to have the highest correlation possible. ChemAxon is developing a training engine that automatizes the descriptor generation, model building, and validation. So it will be a suite for full machine learning workflow. The workflow starts with submitting the training data that is curated and labeled, originating from in-house source and from public sources like Campbell, and the automation will do the heavy lifting, and the user will end up with a new model. It will serve the model management as well. The models can be persisted and executed later on. With regards to feature engineering, we are relying on the high quality physical-chemical properties and all the graph-based and topological descriptors that can be generated with the ChemAxon suite. Here I want to emphasize the pK prediction that was shown to have high correlation with the hERG inhibition, lipophilicity calculation, various atom counts, ring counts, and representation of the chemical structure itself from graph point of the view. But to be able to capture these small structural modifications, we also added fingerprints into our descriptor set. We are building a regression model for hERG using random forest technique with an optimized set of hyperparameters coming from a previous study where we analyzed large set of Campbell targets with random forest technique. I want to quickly introduce you the decision tree itself. Decision tree is a simple statistical tool to predict properties. If you think of a hyper space like this or hypersurface like this with observations on these various planars of the surface, the decision tree is based on splitting of the observations by the features themselves at various points to maximize the homogeneity of the observations. So a decision tree in this case will start with splitting at T1 the observations. If it is T1, if X1 is lower than T1, it will be R1 or R2 category, and we will be in this branch. If it is higher, we will be in this right-hand side branch. What we can split again based on XY at T3. If it is lower than T3, it will be R3. Otherwise, we can split based on X2 at T4. If it is lower than T4, it will be R4, otherwise R5. So we are building a set of decisions automatically to optimize the homogeneity of the data. And there are two crucial hyperparameters: the depth of the tree and the observations in a final leaf that will affect the accuracy of our model. If it will be a shallow model or a deep model, both node size and maximal depths are controlling this. This decision tree or cart is a simple technique that can be used with in combination with bootstraps, which is the resampling of the training data multiple times with replacements and building decision trees for these subsets of the training data and averaging the predictions coming out from these simple decision trees. And as you can see, if the number of trees increases, the prediction will follow even a parabola or complex non-linear curves and correlations and functions quite nicely. Since the mean squared error with the number of bootstraps, with the number of resamplings of the training data, and averaging these weak learners will result in decreasing out-of-bag error and error of the model itself. So we have selected random forest as a technique since it can easily handle outliers, missing data, like pK values will not be available for molecules not having ionization moieties atoms. We have selected for validation of the method the conformal prediction framework, since there is a difference in between traditional programming and machine learning. Traditional programming relying on physics-based methods will be a deterministic approach, while in case of data modeling, data mining, the model itself will be fitted on the training data, and we will have to validate it on test datasets, external datasets, to be able to follow whether the model had an overfitting, and it is only true for the training set. We have selected conformal prediction to be able to predict the error values. The training set is further divided into a proper training set and a calibration set. We are building a model on the proper training set using the features and descriptors, and then calculating the error of the prediction and the observation, and these errors are submitted with the very same feature set, again for a random forest error model building stage. On the calibration set, we are calibrating this calculated error in a way that we are calculating with the model the predicted values, calculating the errors as well, and then we are calculating the observed versus the predicted errors and dividing it with the predicted error and ranking these values and looking for a calibration factor, basically a number that needs to be multiplied with this error to be able to cover 80% of the cases. So we are looking for a correction factor that will scale up the error model for the calibration set to be able to cover 80% of the cases. So not only producing an error model, but on a test set of the error, the calibration set, we are scaling this up. The ChemAxon hERG predictor is a regression model, as I introduced previously, based on electrophysiological data, patch clamp technique. We are using this conformal prediction framework for the error prediction, for error bound, and to be able to further help the users judging the model performance, the top 5 most similar compounds are shown and retrieved with their training data sets. This can help with either ideas how to decrease the hERG affinity, but also to be able to judge whether the result can be used and compared and the molecules can be ranked accordingly. The model offers trainability, and it is seamlessly integrated into the JChem suite and also available in Design Hub ecosystem. We have tested the accuracy of the model with our 200 test set molecules. You can see on the left-hand side the observed versus the predicted values. The green field is showing those the error bound within 0.5 p activity value, while the yellow is the in between 0.5 and 1 p activity error bin. 72% of the cases were observed to have lower than 0.5 p activity, and altogether 90% of the cases were predicted within 1 p activity value. And you can also see the distribution of the delta values from the experimental data here. The root mean square error was found to be 0.55 and the Pearson correlation is 0.8. On top of this statistical evaluation of the model, I'm showing you here some examples how this is following the medicinal chemistry strategies that were introduced previously. So I selected an example structure shown in the middle and calculated the hERG p activity value. It was 6.41. And I changed the surrounding of the nitrogen, the basic nitrogen, by introduction of a fluorine to attenuate the pK, and the pK indeed dropped, the calculated pK drops to round about 2 value, and the model resulted in 6.01 as a predicted value. So the attenuation of the pK value as a strategy from the MedChem toolbox is also reflected in our model calculations. Changing the basic nitrogen to a peptide, to an amide moiety, also dropped significantly the predicted activity. If we are changing the ionic character from basic to neutral, it will be a more hERG liability-free compound. Introduction of a negative charge also decreased the predicted hERG activity, and introduction of a polar nitrogen to the phenyl ring resulted in drop of the predicted value as well. But if we do the opposite, if we are adding a further phenyl group, it yielded an increased p activity value. So altogether, these are small evaluation of the medicinal chemistry rules underlined the prediction power trend-wise of our model. But next, we, from an external publication, from a reference publication, collected 155 FDA drugs. These drugs were deemed to be active or inactive if their P activity value was higher than 6, meaning 1 micromolar inhibition as the threshold value. Running our model resulted in 5 predicted active. Out of them, 2 were indeed in the experimental active category. The rest were inactive, and out of the inactives, 159 were indeed inactives. So this is not the highest performance. The Matthews correlation coefficient was found to be only 0.19. The overall accuracy was 91%, but the sensitivity was only 13%. But here comes the strength of the conformal prediction. Is if we add the error for every and each compound to the predicted value and use this with the 6 cutoff value, with the 1 micromolar cutoff value, in that case, all the 15 active compounds were predicted to be active, and 35 additional compounds were predicted to be active, although none of the molecules predicted to be inactive were found to be active. That concludes to a Matthews correlation coefficient of 0.48, accuracy of 80%, and 100% selectivity. So the strength of the model is that it is a continuous prediction. And from that, as you can see, by changing the thresholds, you can decide on the risk mitigation. You can balance the trade-off in between sensitivity and specificity. And by adding this error, you can achieve higher performance on this classification use case. In the reference publication, the sensitivity of the best model was found to be 71%, and the specificity was similar to the specificity what we observed, while the balanced accuracy, which is the average of the sensitivity and specificity, was found to be 75%, which is, in our case, round about 89%. The other way how you can mitigate the risk with this continuous prediction is that you can subtract the average error and use that as a more strict criteria. And I subtracted the average error, this 0.6, from the 6 value. And with this method of the evaluation, again, all the 15 actives were found to be in the active category, less inactives were in this predicted active category, and all the predicted inactive were found to be inactive. Again, 100% sensitivity was observed, a bit increased specificity. But this tells something about the accuracy of the regression model itself, that in the top 44 we could identify all the active molecules, and beyond that, or lower predicted activities were all found to be inactive. But still, when you are applying a model in-house with never seen chemistry, new ring systems, new molecules, you fit the model on these local sets, and it can be used for interpolation and for close analogs. But when you are moving away with new derivatives, new chemical moieties, there will be chemical spaces unseen by the model. The model might be blind to that chemical series. What we recommend is continuously retraining the model to be able to have the highest accuracy, and that's one of the features of the hERG predictor, that it's not only a predictor that you can retrain with your local own data to maximize the accuracy of your prediction. But the last point is how the model can be utilized in medicinal chemistry projects. Since in medicinal chemistry projects, chemists need to focus on various parameters at the same time and needs to call all the services resulting in predicted values, database searches, freedom to operate, what is available in vendor catalogs, and how this is embedded in the project context, how my series can be triaged, evaluated next to other series. And for that, we embedded our predictor to the ChemAxon Design Hub, and András Stracz will tell you how predictions can be utilized in a design context in the next episode of this webcast. Thank you for your attention.
Our next presenter is András Stracz. He is a computer scientist who joined ChemAxon in 2009. Since then, he worked on advancing ChemAxon's web-based products such as ChemicalEyes or the early versions of Plexus Design. In the last few years, he has been the product manager of Design Hub. András, the virtual stage is yours.
Thank you. So in this segment of the webcast, I'd like to talk about how we can apply this new hERG predictor in a lead optimization application called Design Hub. First, we are starting on a target, IREC4, which has been recently discussed quite a lot in publications, like this Medicinal Chemistry Reviews paper, from which we pulled out a couple of really illustrative images on a core compound, which we have broken up into several parts as our investigations and our further rational designs. You can see that with the purple highlights, it has this amide group. That's going to be kind of its scaffold, and we're going to try different methodologies to provide alternatives to like the western part, southern part, northeastern part, and see if we can improve the interaction with the highlighted key residues. We have even broken up the chemical structure into some parts to create these R groups, and we have created a couple of these scaffold ideas which have acceptable alignment with the original co-crystallized ligands. So with manual design or enumerations or new de novo design tools, it would be fairly easy to imagine that you can create a bunch of ideas. Here I have outlined a couple of ideas that we can think up, like different variations in like this southern part. You can see different variations here, or different variations to the what was called the eastern part of the compound. How do you select from these? Well, the answer should be fairly obvious. You need to look at all of the available data that tell you what's the synthetic feasibility, what's the freedom to operate, how do the various basic metchem properties of the compound look like, and whether there is off-target activity. And you will do this for every single compound idea that you have in a set, right? So that's what we're going to continue with now. Inside our application Design Hub, you can see all of these compound ideas laid out on these cards in a very similar arrangement, and we have run all these calculations and predictions and searches for the compounds. You can see that we have access to the basic medicinal chemistry properties. I've selected CLOC P and PK to be displayed here. We have hERG predictions here from the new ChemAxon hERG predictor, and we have a Schur-Campbell similarity score as well, a higher similarity score. We have sorted the compounds already based on hERG, and you can see that the compounds are in a general like 5 to 6 predicted PIC50 range. So this is one way to use the predictor. It is going to provide us this low resolution information, just the numbers. And we can use that to sort our ideas, to filter them even. But there is another way, and that's when we select one of the compounds of interest, something that we particularly liked from the set, where we go to rich visualization mode. So here on the right, you can see that we are displaying the hERG activity, but we also display the predicted error, conformal prediction that goes with it. And we are also displaying the most similar or most relevant training compounds from the training set that was used to train the model. This is the applicability domain. And with this information, it should be much easier to argue about a compound and argue about how you trust or distrust the prediction value. I have also put Schur-Campbell data there with a higher resolution, so you can see the most similar results from the exemplified structures in that data collection. And with this way, we can come up with our own weights to these decision factors, essentially. If I switch to a different compound, which has a couple of different differences to the original one, you can see that the information is slightly different. Schur-Campbell score is higher, while our hERG activity may have been predicted to be more advantageous. So we can use these factors to come up with our cutoffs and with our preferences. So I have applied these as filters actually on this next screen. You can see that we are filtering to a maximum allowed kind of similarity score of 0.85 and an okay hERG liability of 6. Based on this, we can prioritize our compounds, which is the goal, to figure out how we're going to allocate resources for the colleagues. So we are doing this using a plugin system that is part of the application, to which we can plug any application from any vendor on any interface or with any programming language. And this is a method we can use to help chemists filter their compound ideas or go into use case specific kind of rich visualizations that are tailored to those use cases, be that colored numbers with conditional formatting and whatnot, or chemical structures with similarities scored laid out in a grid or even a chart. This supports all the latest technologies, so we can approach this topic from like a deployment perspective as well, and look at how we can do serverless infrastructures with AWS Lambda Fargate. And there's a lot of examples, so creating new ones is expected to be a very simple job. And indeed, since this new ChemAxon hERG predictor offers a REST API, we had a really easy time creating this integration for the purposes of this webcast. But there is something else that I want to touch on as well, which is that the plugins can really act as complementary tools to one another. So there is one more plugin that I would like to show you in detail, and that's called a hERG Assistant. This is specific to Design Hub, and its purpose is to show how we can use data sets that cannot be easily modeled with continuous regression models or anything like that. For that purpose, we have selected the patch clamp assay that is published on Campbell for hERG, and we have created an MMP data set or database on top of that. So match molecular pairs is a statistical tool that tell you what chemical transformations have what statistically significant or insignificant associated activity change in the compounds. As you can see on this simple one on the left, that we are able to show that for this particular functional group transformational replacement, we can see 6 examples in the training set, where the minimum PIC50 change was -1. The maximum change that we have seen was 0.44 with a median of -0.5. And we can also display example compounds where the transformation is applied to an idea. So in the data set, right now we have about 200 transformations that occur with a high frequency in the training set. And we can use this to determine if it provides a way to get out of a suspected hERG liability, and whether the new hERG predictor suggests a kind of a correlating change on the predictions. So going back to my set of ideas, there is a particular subseries that I would be interested in, these macrocyclic ones. So the issue with the macrocyclic ones is that due to their weight, molecular weight, and due to the predicted activities, they fall somewhere to the second half of my sorted list. They definitely do not appear to be as advantageous overall. But let's see what our hERG assistant provides as a potential suggestion. So here I have paged through a bunch of the suggested transformations. And if I stop on this hydroxymethylation example, then that actually gives me a clue on what I might be able to do. Because it suggests that if we put this hydroxymethyl group on the compound, then there is a good chance that it will lead to a half log unit decrease in our predicted activity, hERG activity. So we have made that change. That's how it would look like. And indeed, what we're able to see is that the change direction is backed up by this hERG predictor, although the magnitude of the change is a bit less. So it's 0.2 with a slight reduction in the predicted error as well. But still, we like that. And this could be another compound that we add to our collection. So in addition to following the typical medicinal chemistry strategies of looking at PK attenuation or controlling lipophilicity or whatnot, we get these kind of semi-automatic suggestions as well. And it's really nice when we can see that the different plugins can complement one another. We can see different changes, of course, for sweet spots. So this is a problem we can continue to really to like a really detailed investigation, which is part of the typical work, which is why this is an NPO problem. Addressing one adverse effect might lead to others. But this is where I would kind of stop. The purpose of this demonstration was that we are able to effectively use the new hERG predictor within a replication to filter out and to rank compounds with respect to their off-target activities. The application otherwise provides a full workflow solution here, starting from the original hypothesis and the original kind of sub-project on which we are trying to optimize these compounds, include our breakdowns into what a different chemical series might include, and all the way to tracking the ideas as we are discussing them with the colleagues or bringing them through synthesis. So that's the Design Hub story in a nutshell. And if you're interested, find us to learn more. Thank you.
Thanks, András. Dear audience, thank you very much for attending. We hope to see you on our upcoming webcasts and also at our online community on LinkedIn. Our platform is called ChemAxon Users Group, a closed group for verified users to ensure the quality of conversations. So once again, you will need to search for ChemAxon Users Group on LinkedIn. This group is our informal community where you can ask your questions, share your opinion, and you also connect with speakers and peers. We look forward to seeing you there and on our upcoming webcasts. Stay safe and goodbye.